Welcome to Chapter 2, the chemical level of organization. Remember in Chapter 1 we discussed that basically everything on Earth, including us as organisms, are made up of chemicals, and that's going to be our main topic this chapter, chemicals, and then we're going to build that into cell parts and cells for Chapter 3, and then we'll build on the tissues and finally get into our organ system. So we're starting with the small basic components of all life in chemicals. Once again, at the beginning of every chapter, you're going to find these learning outcomes. These are a really great foundation or a great base for your studying for your exams. Please make sure that you can answer all of these by the end of the chapter. Some more learning outcomes and one more page of learning outcomes. Okay, first section is regarding elements and atoms. So I'm sure some of you have seen this table before. This is known as the periodic table, and we're going to be covering about 4, 5, 6, 7 of these in full detail this semester. We'll hit some other ones, what we call the trace elements, and anatomy and physiology too. By no means do you have to memorize this table, but basically all of the elements that exist on our planet Earth come from this table. And you'll see a bunch of gases and solids and liquids in this table. So first, let's get some terminology down. All of those things that you saw on that previous slide, the periodic table of elements. So you saw an H, which stands for hydrogen. You saw an O that stands for oxygen. You saw a Cu that stands for copper. All of those are known as elements. And as you can see in the slide, these are the building blocks of matter. So whether we're talking about cells and tissues, or a tree, or a big steel bar that goes inside of a building, all of those are made up of some type of element. So everything in the universe, solid, liquid, gas, has to come from some type of element. Now, these elements exist in very numerous forms, or there are numerous elements. For example, when you breathe in oxygen, there are millions of oxygens around you, and what we refer to those as atoms. So I'm breathing in the oxygen element, but I'm breathing in millions of oxygen atoms when I take a deep breath in. So this is the smallest quantity of an element, and they show the properties of that element. So for example, oxygen is a gas, so all of the oxygen atoms are little tiny gas particles. Now in chemistry and in our body, what we like to do is we like to combine several of these atoms. And when we put two or more different elements together, we get something called a chemical compound. And you can see the example here on the bottom. One that we're going to talk about frequently is salt, NaCl. So the Na is sodium, and the Cl is chlorine. And when you put them together, they create this ionic bond, which basically means that electrons, the small particles on the outside of the atom, are stolen or moved from one another. They create this bond, or this kind of magnet effect, and they become a different structure. So sodium, for example, very, very toxic. Chlorine, also toxic, right? You don't want to drink the pool water or anything like that. That's not going to be good for you. But when you put these two somewhat toxic elements together, they neutralize each other, and it becomes table salt, which is actually really, really healthy for you. We need salt in our diet for muscle and nervous system function. So that's called a compound because we have a sodium atom, or a sodium element, and we have a chlorine atom, or a chlorine element, put together to make something bigger. And then our last example on this slide is a molecule. And a molecule is just where two or more atoms are held together by something called the covalent bond, which basically means they're sharing electrons. They're not really stealing. And you really don't need to know the difference between the two, ionic and covalent, or what's stealing and what's sharing. But a great example of this is where you have the same element sharing multiple atoms. For example, O2. Nitrogen is another one as well. Molecule, N2 nitrogen molecule. So what we're going to have is multiple atoms put together, and generally speaking, without getting into too crazy detail with the covalent bonds, is they share the electrons together to make sure that they are stable. So oxygen by itself, if you just have an O, it's actually very unstable, not very good for us. So what happens is another O comes together with it, calms it down, and that's what we typically breathe in all the time, every day, is O2, oxygen. So another example of a molecule, one that you're familiar with, is a hydrogen atom that's combined with another oxygen atom and a second oxygen atom. And what we call this is H2O, water. But what it is, it's simply two or more atoms held together by this specific type of bond where they share the electrons. So on that periodic table of elements, you see that there's over 100 elements that exist. And a lot of those are found in our body, believe it or not. You have copper, you have silver, you have actual gold in your bloodstream, believe it or not. Very, very, very small amount. But the majority of those elements do exist in our body in one form or another. However, the majority of your body can be summed up in 4 to 6 elements. So you can see that 99% of the mass of your body is made up of these 6 elements. What I really want to point out is the top 4. And these first 4, carbon, hydrogen, oxygen, and nitrogen, and you can see what they're abbreviated or symbolized with in the periodic table. O stands for oxygen, C's carbon, H hydrogen, and N nitrogen. These 4 make up 96% of your body mass. So if you weigh 100 pounds, 96% or 96 pounds of that 100 pounds is carbon, hydrogen, oxygen, and nitrogen in some way or form. If you weigh 200 pounds, over 190 pounds of you are these 4 gases. Now, I know I'm leaving off the calcium and phosphorus, and these are very, very important, especially for muscle nerve function. With calcium, also your bones. But as you can see, if you do the math, the calcium and phosphorus put together is really only about 3% of your body mass. So these first 4, carbon, hydrogen, oxygen, nitrogen, those are the big ones. That's the 96%. And the way I always remember this in school was if you move the letters around, they can spell something to help you memorize the 4 big ones. I always remember CHON, so C for carbon, H for hydrogen, etc. Or if you want to move them around some more, you can spell notch without the T. And that just shows you that these 4 elements make up 96% of your body. Now, what's the other 1%? If calcium and phosphorus equal 3%, which gives us 99, the other 1% is pretty much everything else. You can see that there are some trace elements, what we call. Well, we'll get to more trace elements later on, excuse me. These 5 elements do exist. They make up the majority of the remaining 1%. You can see we have potassium, sulfur, sodium, chlorine, and magnesium. But we'll also talk about a few others, such as iodine, very important in our body. We'll talk about iron as well next semester. But a big, big portion of them, 96%, is carbon, hydrogen, oxygen, nitrogen. Now, what's really cool, before we move on to the next slide, take a look at this. Our body, typically, if you just Google how much of our body weight is water, right, you're going to get different numbers. And it really just depends on your weight, how much fat mass you have, how much muscle mass you have. But what you'll learn is the majority of your body is H2O. And you'll see numbers anywhere from 60 to 80%. If you're really athletic and you have a whole lot of muscle, you might be in the 75-80% range. Not so much, you might be 60%. But notice H2O, water, look where we're getting this water from. 96% of your body is made up of carbon, hydrogen, and oxygen. So it makes sense that a big portion of your body is water because 2 of the 4 main elements in your body is what makes up water. So keep that in mind because we're going to be talking about water a lot in just a second. Before we talk about water, let's talk about different compounds. Remember what a compound is? It's just when we're getting 2 different atoms together and they're forming this kind of different special bond where they change properties. The big one we used earlier was sodium and chlorine. So we have a sodium atom by itself, a chlorine atom by itself, and we're going to combine them to make a sodium chloride compound or a salt compound. So first off, before we discuss the details of the different compounds, let's get some terminology straightened out. As you can see, inorganic versus organic compounds on the top of your slide. Inorganic compounds, the key word, the key difference between these 2 compounds is carbon. So when you see organic in regards to chemistry, that doesn't mean that it's natural or that it was farmed on an organic farm. That's a little different meaning. Organic in relation to chemistry is just carbon. Does it have carbon touching other things? So you look at the definition of inorganic on this slide. Typically speaking, inorganic compounds are really, really small, simple, such as sodium chloride. We have a sodium atom, a chloride atom, 2 atoms, boom, done, that's it. They're not really, really complex. Another example is water, right? We have 2 water atoms, and then we have 1 oxygen atom, so we have 3 atoms together. And it's really, really small. 3 atoms, not that big, microscopic, and they don't contain carbon. So they would be considered inorganic. Now, let's get a little more detailed and look at the exact definition of inorganic. Usually does not contain both carbon and hydrogen. So in both of these examples that I gave you, water and NaCl, neither of these compounds have carbon in it, period. But what really happens, the difference with organic and inorganic is with an organic compound, what we're going to see is carbon is going to be bound or touching another carbon or a hydrogen molecule, or hydrogen atom, excuse me. So in the case of something like this, where we have C, carbon, and 2 oxygens, carbon dioxide, yes, we do have carbon, but look at the definition. We are lacking hydrogen here, and we're not connected to another carbon or another hydrogen. So although CO2 is containing a carbon atom, it is still considered inorganic because it's not bound to another carbon or another hydrogen. So what's an example of an organic compound? Well, easy one to talk about is methane gas. Methane gas is CH4, so it's a carbon, and that 1 carbon is bound to 4 different hydrogen atoms. So if you look at our definition of organic, it's a carbon connected to either another carbon or a bunch of hydrogen atoms. If you take a look at another prime example that we're going to spend a lot of time on is sugar, also known as glucose. And the molecular formula for sugar is C6H12O6. So you can see we have a lot of carbons here, 6 carbons, and they are also connected to a whole boatload of hydrogens. So that would be considered an organic compound. So take a look at the difference between these molecules, or these compounds that I just illustrated. I'm drawing kind of a blue line between the two. Count the atoms in all of the organic compounds that I wrote in red. So CO2, we have 1 carbon, 2 oxygen. So we have a total of 3 atoms. Let's count the hydrogen, or the H2O, the water. 2 hydrogens and 1 oxygen, so that also equals 3 atoms. Here we have NaCl, so that's only 2. So these are small, not that many atoms, they're pretty simplistic. Take a look at the organic compounds that I drew down here though. CH4, we have 1 carbon and we have 4 hydrogens, so we have a total of 5 atoms in this compound. Still a small number, but more complex than 2 or 3, right? We're getting a little bigger. Take a look at glucose, which is a very small molecule, a small compound, but take a look at all the atoms. We have 6 carbons, plus 12 hydrogens, plus 6 oxygens. And if you do the math there, we're talking about 24 atoms. So organic compounds typically tend to be a little larger, a little more complex. They have more atoms in them compared to the smaller inorganic compounds. Now, both of these are very, very important in the body. We need carbon dioxide, we need water, we need salt. Without those 3 things, we will die, or you'll have some serious issues. And we also obviously definitely need sugar in our body, otherwise our blood sugar, blood glucose would just plummet and our brain would shut down. So all of these are important, but before we dive into the importance of them, I wanted to show you the differences between them all. Okay, water. Very, very important topic. As you can see, water is the most abundant compound in the body. I mentioned, depending on your muscle mass, you can have up to 60, 70, even 80% of your body mass are just these 2 atoms combined in this fashion, H2O, water. Very, very important, the majority of your body. Now, water has numerous functions in our body. As you can see, there are 4 or 5 bullet points on this slide. These are just 4 or 5 kind of big ones, but we can go on for 20, 30 bullet points talking about the importance and the details of what water does in the human body. It's extremely vital. But let's talk about these 5 big ones, because this will be a really important and recurring theme as we continue throughout the semester. So first off, water is a very good lubricant and cushion in the body. And a great example of this is what we talked about in chapter 1. If you remember all of those cavities, we talked about the pericardial cavity and the pleural cavity and the abdominal pelvic cavity and the cranial cavity and the superior medial sternum. All of those cavities have those 2 layers. And this will be a really good review for you. What are those 2 layers called that surround, those little sacs or bubbles that surround all of our organs? So we had a superficial one, and that was called the parietal layer. I'll just put P for parietal. And then the one that's actually touching the organ itself, or the deeper membrane, the deeper lining, was called the visceral membrane. So we have these 2 membranes surrounding these organs, and there is fluid between these. And guess what the majority of that fluid is made up of? Guess what the main ingredient of that fluid is? You guessed it, it's water. What we call this is something called a serous cavity, or what we call serous fluid, and it's mainly water. The water in between your joints. You have something called synovial fluid in between your shoulder and elbow and wrist, your hips, knees, ankles, toes, fingers, all those things. And the major ingredient of that fluid to help lubricate and make sure that joint is okay and the bones aren't grinding next to each other is called synovial fluid, and that's mainly water. Your blood is at least half water if we're somewhat healthy. The fluid that's protecting your spinal cord and your brain, cerebrospinal fluid, is also majority water. So very, very important. It cushions us. It protects you. If you did not have cerebral spinal fluid surrounding your brain would cease to work. It would literally just kind of cave in on itself, and therefore you would not be living, right? So very, very important. Cushions us, lubricates surfaces, makes things slippery. So, for example, when I go out and exercise, I go run a mile or two, my heart starts pumping more violently, right? Surrounding, kind of squeezing down on the heart, are my two lungs on either side. But the reason why my heart doesn't actually physically touch or rub against my lungs is because of the parietal layer and the pericardial cavity and the visceral layer surrounding the lungs. Well, sorry, it'd be parietal for both. Parietal layer for the pleural cavity and parietal for the pericardial cavity. But those two cavities, those two membranes, are what's actually pressing against one another, and they are designed to be a lubricant. So they're okay. So your heart doesn't get swollen or inflamed. You won't get a blister, right? Picture running outside with no socks and brand new shoes, you might develop a blister. Your heart and lungs would also develop blisters if we didn't have this cushioning or this slippery lining between the organs. So that's just one thing that water does. Let's move on to the second bullet point, talking about transportation. As I mentioned, half of your blood, approximately, is water. So it's basically, your blood is kind of like a lazy river, but it's a fast lazy river. And you have all these different types of cells, or these things floating in it. You have red blood cells, you have white blood cells floating in it. You have platelets, you have a bunch of proteins, you have sugar from your diet, all these cholesterol, all these things floating around, hormones. And how they actually float and get around the body is through the bloodstream. And your blood has to be in liquid format in order for it to do this. So water, being half of the blood, helps us accomplish this. If your blood was not made up of at least half water, we'd have an issue, right? All those red blood cells, white blood cells, they would kind of get stuck and kind of clump up together. And that can happen in severe situations, which could cause some serious issues. But other things that are transported in the body, just from a cellular standpoint, the majority of the fluid inside your cells are water, or is water, excuse me. And the majority of the fluid outside of your cells is water. So as we are delivering packages, moving proteins back and forth, delivering hormones to the cells, moving cholesterol here and there, all of that is traveling through water. So if the inside of your cells, your billions and billions of cells, are made up of mainly water, and the stuff that's not cells on the outside is mainly made up of water, and your bloodstream and your cerebral spinal fluid and your joint fluid and your cavity fluid is mainly made up of water, now it doesn't sound so crazy when we say that the majority of your body is made up of water, because the majority of the things in your body are made up of water. The third bullet point, in regards to functions, talks about the high heat capacity of water. So what does that mean? Well, it takes a lot of heat to affect water, is what that means. So, for example, picture we're making some pasta for dinner, and we need to boil some water, right? So let's put the stove on low, and let's just put a pot of water on there and just let it sit, right? If it's on the low setting, it's probably never going to boil. Yes, it's going to get warm. It's actually going to get hot. You can burn your hand on a low setting, but water needs a little more oomph, a little more kick to it, right? It's pretty strong. So you have to put it on high in order to generate enough heat, enough temperature in order to change water. Because water in our body, for the most part, is in a liquid state, liquid format. In order to change liquid into gas, we need to really pump up the heat. And the actual, to boil your water, is 212 degrees Fahrenheit. And as some of you may know, our normal body temperature, give or take a degree, is 98.6. So you need to more than double the body temperature in order for the water to change from liquid to gas. So water is really, really good at kind of being itself and doing its own thing, not being changed too drastically. And we can actually use that to our advantage. We can kind of manipulate water as it absorbs heat very well. So you can heat water up to 180 degrees, 190 degrees, and it's not going to boil. So we'll talk about this more in the skin chapter, but if we need to sweat, we can actually move water around in our body, specifically through the bloodstream, to kind of change our heat distribution. And same thing versus if we're getting cold, we can actually move water around our body to retain heat in the important areas such as our heart and our kidneys and our brain, and make our other parts of our body a little more cold, like our skin. So we'll talk more in detail about that, but water is really, really good at maintaining its properties. The next bullet point with water is it's an excellent solvent. Which means that most things mix very, very well in water. If you go get a jar or a glass of water, you can pour almost anything in it, and it's going to mix pretty well. Pour a bunch of salt in your water, and then just kind of stir it up and shake it a little bit, and that's it. You don't even know what's in that water, right? Go to the lake and then go to the ocean. The water looks the same, right? But if you drink ocean water, you know it's going to taste drastically different, right? The salt is dissolved in the water. Let's put sugar in the water. Make some tea, and then dump 2 tablespoons of sugar in your tea, and mix it up. And you don't see sugar floating in the water. It dissolved. It mixed well in the water. And we can talk about anything. Food coloring, anything really mixes well with water, except for one very important molecule or compound. And for some of you who cook from time to time, you'll know that fat, or what we'll refer to in this case right now with cooking, is oil, which is a fat. These do not mix well with water. And that's going to be extremely important in just a little bit, but even more important in Chapter 3 when we talk about the anatomy of a cell. If we have trillions and trillions of cells in our body, and the fluid on the inside is water and the fluid on the outside is water, how do we make sure that that water is just not mixing back and forth so our cells shrink up or blow up and pop? Well, we have to make a barrier that's not really friendly with water. And what you'll see is that layer is mainly made up of fat. So fat's a good thing. We want that in our diet. We actually want a good portion of that in our diet. And one of the main reasons is because of this. We want to be able to control the compartments of water. And then last, but definitely not least, our metabolism. A lot of our chemical reactions stop and start with water. We can't have this without water. So remember our definition of metabolism from Chapter 1. We have building things, which we called anabolism, and then we have breaking things down, which we called catabolism. You can't build things without water, and you can't break things down without water. And as you'll see, slide 20, we're going to get to it eventually. We have a few more slides before we actually show you the details of how water is involved with this. But if you're trying to build muscle or repair a broken bone or break down the food you just ate for lunch, you can't do that without water being present. So before we move on to the next slide, just kind of take a step back and just look at all these things we talked about, why it's so vital, why this keeps you alive, right? You can go 2, 3, 4, 5 months without food. Are you going to be comfortable? No. You're going to not feel well. But you can survive several months without food. You can only go a couple days without water. I mean, just look at it. It lubricates, cushions your body, transports important nutrients, red blood cells, oxygen throughout your body. Make sure that you don't overheat or that you don't freeze to death. Mixes with all the chemicals that we put in our body constantly. And builds and breaks things down, which we constantly need to do in order to maintain our equilibrium or homeostasis. So very, very important. We'll be discussing water in great detail this semester. So stay tuned. So for the next 2 slides, we're going to be discussing specific types of inorganic compounds. Once again, very small compounds, and usually they do not have carbon associated with them. And electrolytes are very big examples of inorganic compounds. And what an electrolyte is, I'm sure most of you have heard of an electrolyte, and generally speaking, what we think of is salts, right? We think of sodium chloride, potassium chloride, that kind of thing as an electrolyte, and you are correct, those are electrolytes. But what an electrolyte is really anything that breaks up in water. If you dump it in water, it will dissociate, or it will separate, and with it, it will carry an actual electric charge. So if you take a look, for example, let's draw NaCl, or write NaCl. Once again, this is a compound, 2 atoms, so a sodium atom and a chlorine atom. And when they're together, notice that there's no pluses or minuses. It's neutral, they're balanced, it's good. But when you break these two apart, what happens is you get these things separated, sodium and chlorine, and notice it's got a plus, it's got a charge to it. And then chlorine here has a minus. So notice the charges there as well, a plus and a minus. When those two get together, they kind of balance each other out, and that's why sodium chloride is neutral. And you can see the same thing here in this example with magnesium chloride. Magnesium, we use 2 chlorines, and they're balanced, there's no positives or negatives. But when they separate in water, we have 2 plus charges with the magnesium and a negative charge with the chlorine. And that's why we need 2 chlorines to balance it out. So an electrolyte is anything that carries an electrical charge, or basically an electrical current when mixed in water. And remember, with the previous slide, the majority of your body is water. So if we have a bunch of these things floating around in water, this is how our body runs on electricity. So you take a look at the 2 main functions here, muscle contraction and nerve impulses. Your body literally runs on electricity. When your brain tells your fingers to move or tells your mouth to move, there is a whole bunch of electrical sparks that are sent down from the brain to the brainstem, to the spinal cord, out to the nerves that talk to the muscles. So literally it is electricity. Your muscles, without proper electrolytes, they either stop contracting or they contract too much, right? We've all had a cramp or a spasm back in the day, and that's usually due to an electrolyte imbalance. So think about if we're having a heart attack. If somebody is, their heart stopped and they're down on the ground and they're not really breathing that well and their heart's not beating, we need to do some CPR, give them some oxygen, right? But what we're going to eventually do is shock them. We're actually going to generate an electrical voltage and put electricity into their body to jumpstart their heart. So even the heart, being a muscle, runs on electrolytes, runs on electricity. So we'll talk about a lot of these this semester. Sodium, potassium will be huge, even in this chapter, or in this module, chapter 3. We'll talk about chlorine a little bit. We'll mention calcium a lot with the bones, big time, and also with the nervous system and the muscular system. So we'll talk about a lot of these electrolytes. But these are all inorganic substances that have an electrical current. Last examples we want to show you with organic compounds are 2 respiratory gases, very, very important, keeps you alive, mainly oxygen, right? Oxygen, as we said earlier, is O2. Oxygen by itself, kind of upset, kind of imbalanced, toxic, if you will, and not very stable. But when we put another oxygen with it, it's very balanced, stable, good, happy, healthy, and that's what we typically breathe in. And that's what's giving us energy for all of our cells. It's also what's keeping you alive in regards to your brain, your heart, your kidneys, that kind of thing. Carbon dioxide gets kind of a bad rap because we have to breathe that stuff out. It's our waste product. But we do need a little bit of carbon dioxide in our body at all times. If we don't have any carbon dioxide, period, we can have some brain memory issues, and our body will start to break down. So there's just a balance. We just can't have too much of it. So what we do is we breathe that out typically, and the really cool circle of life part of this, if you will, is that the plants use carbon dioxide like we use oxygen. So we need oxygen to survive. We make CO2 as kind of a waste product. The plants need carbon dioxide to survive, and they kind of give off oxygen as a waste product. So it's a very happy, healthy relationship between all of our flowers, trees, plants, bushes, all the green things throughout the world. Help keep us alive. Once again, these are both inorganic compounds. Yes, CO2 has a carbon in it, but it's not bound to any other carbon or hydrogen. So this is considered inorganic. Plus, it's just a really small compound, right? There's only 3 atoms. So typically anything 3 or less is going to be inorganic. Okay, so we've covered atoms, we've covered composition of the body, we've covered inorganic compounds. The remainder of this chapter, and as you can see, we're just getting started here. The leftover part of the chapter is all about organic compounds. So what this is going to consist of is a carbon bound to a whole bunch of other carbons, and then a lot of these carbons will have hydrogens on them as well. So these are going to be a lot bigger, larger compounds, excuse me. Alright, the 4 major types of organic compounds are also known as macromolecules. And if you've ever been on a diet, you've heard of the 3 major macros: carbs, fats, proteins. We're going to add a 4th macro that's pretty much in everything that you eat for the most part, and that's nucleic acids. So these 4 major organic compounds make up the majority of your body. And if you look at the building blocks of these, it's going to hopefully come full circle for you and make perfect sense. Carbohydrates. You think about pastas and cereals and fruits and veggies. Main ingredients of carbs is carbon, hydrogen, and oxygen. And remember our cool little formula for sugar, which is a simple carb, C12H12O6, so that kind of makes sense. Fats, very important for our body. Main ingredients of fat, or main elements that make up fats, are also C, H, and O. You see a theme here, you see a pattern here. Look at proteins. Main ingredients of a protein is CHO, and then that's where we get that nitrogen from. So you see the chawn or the notch. Same thing with nucleic acids. Main ingredients, CHON. So, once again, 96% of our body mass comes from these 4 elements: carbon, hydrogen, oxygen, nitrogen. And you can see the 4 macromolecules, the 4 major organic compounds in the body, are made up of these 4 elements. Proteins and nucleic acids, the only one having nitrogen, but C, H, and O are found in all 4 of them. So what we're going to do for the remainder of the chapter is we're just going to dive into each one of these 4 major organic compounds, learn about what they are, what their function is, why do we need carbs, why do we need proteins, the building blocks, that kind of thing, and how we build and break these structures down. So let's get started. We're going to begin with carbohydrates. Carbohydrates, typically, at least in the past few years, have gotten a really bad rap. People go on these low-carb diets, or the ketone diet, where you don't eat typically any carbs. And short-term, you can see some cool results, yeah. But long-term, your body really likes this stuff. And the majority of people back in the prehistoric, historic, whatever time frame you want to see, you go to other countries, the majority of other countries who have pretty much healthy people, they eat a lot of carbs. So, very, very important. And the reason why is carbs is not only the major energy source for our body, but it's actually the preferred fuel source for our body. And specifically, when I say preferred, we're talking really about your brain and your red blood cells. They love sugar. They love carbs. And you think about these two things, the brain keeping everything going, right? Homeostasis doesn't exist without the brain. And then without your millions and billions of red blood cells, you don't have any oxygen to help your brain survive, or your liver, or your pancreas, or anything else for that matter. So if these two structures in your body that are keeping you alive 24/7 prefer sugar, it makes sense that sugar, or carbs, is a very vital part of your diet. Now, where we get messed up in America specifically is we just eat too much of this stuff. We eat an entire loaf of bread or an entire pizza by ourselves, or after dinner, we eat 3 scoops of ice cream instead of 1, right? And what happens is when your body has too many carbs, we store it temporarily, but when we store too much storage, it eventually will turn into fat. And that's where we get the bad reputation from, is, oh, carbs make you fat, carbs make you heavy. Well, actually, if you eat too much of anything, it will make you fat. If you eat too much fat, you will gain weight. If you eat too much protein, believe it or not, you will gain weight. So go ahead, eat a 50-ounce steak. Your body's only going to break down about 20% of that, or 40% of that. The other part will be excreted in urine, hopefully, or it will be turned into fat. So even lean, quote-unquote healthy meats can be turned into fat if you eat too much of it. So once again, homeostasis, balance, a very important theme in anatomy and physiology. So main ingredients or main elements of carbs, we introduced that on the previous slide: carbon, hydrogen, and oxygen. There is no nitrogen in carbohydrates, but the other 3 big elements, CHON or NOTCH, they are involved with carbs. And what carbs are often described as or called are saccharides. And a saccharide, as you can see, is simply sugar in Greek language. And a lot of these anatomical terms that we talked about last chapter was either from the Greek or the Latin languages. So saccharide means sugar. So you put a whole bunch of sugars together, you're going to get carbs, or sugars are known as simple carbs. And if you put a whole bunch of sugars together and they digest slowly, sometimes they're called complex carbs. But carb, sugar, kind of synonymous. And we have different types of sugars. I'm sure you've heard of glucose and fructose and lactose and sucrose. Not that you really need to know the difference between them, but if we have one sugar by itself, that is what we call a monosaccharide. Mono meaning one. And an example of that would be glucose, just one sugar. If we have 2 sugars combined, for example, if we put a glucose with another monosaccharide, such as galactose, which is a sugar, that's what when we combine them, they're called a disaccharide, di meaning 2. And that actually equals lactose. For those of you who are lactose intolerant, it's those 2 sugars combined that give you a hard time. And then last but not least, if we put a whole bunch of sugars together, if we put lactose with another lactose, or with a fructose and a glucose, or yada yada, we get something called a polysaccharide. And that's just 3 or more. It can be 3, it can be 30, it can be 1,400. It doesn't matter. It's just as long as it's more than 2, we're going to refer to that as a polysaccharide. So once again, a monosaccharide is just a 1 sugar compound. So common example is glucose, but some of you may have heard of some of these other ones, such as dextrose, ribose, deoxyribose. We'll talk about that with the nucleic acids. But if you notice a cool theme here, all this stuff kind of ending in ose: glucose, dextrose, deoxyribose, galactose. Anytime you see this suffix ose, typically we're going to be talking about some type of sugar. And you'll see that on the next slide when we introduce disaccharides as well. Big key word here on this slide is something called a monomer. And what a monomer is a building block. So it's kind of like one Lego block. If we're building a tower of Legos, or a building of Legos, all of the individual Lego blocks are what we would call or refer to as monomers. So as I mentioned earlier, if you put a whole bunch of sugars together, we're going to get those kind of bigger polysaccharide, more complex carbs. So the building blocks of all carbohydrates, whether we're talking about your carrots, your pasta, your donuts, your pizza, your ice cream, whatever has carbs in it, all of it has monomers in it, sugars. Now these sugars can be combined to form other sugars, but for the basic building block of all carbohydrates, they are made up of sugar. So why is a sweet potato healthy for you? Well, your body hopefully breaks that sweet potato down into monomers, into sugars. And once again, what thrives on sugar is your brain and your red blood cells. So we need that. So whenever we eat something, even if it's just like a bagel, we're going to break that down into its simplest components and absorb it in the bloodstream. And the reason why we have to break it down into its simplest components is those blood vessels in our gut are very small. So we can't get these big molecules into these tiny little blood vessels. It's very hard to do that sometimes. Also, it's just easier if our body's smarter than we are. If we break these things down to its smallest components, our body knows what to do with them better than what we consciously know what to do with them. So we're going to break that bagel down into its simplest sugars, and that's going to give us energy and help us repair tissue and do other really cool things. But main thing is energy for your carbs. Other types of monosaccharides you can see here, you have different, when the elements fold, we're going to talk about folding of specifically proteins in just a little bit, but they do make these three-dimensional shapes. These aren't just flat paper-like structures. They do exist in 3D, so they can make these kind of hexagon-looking structures or these pentagon-looking structures. And the big thing I just want to point out here on this slide is they still, once again, they're all sugars. They all end in this suffix -ose. But when we get to our DNA and our RNA, when we start talking about our genetic material and stuff that helps us make proteins, these are a little different. They're kind of in this pentagon shape called pentoses, where typically the other sugars that we eat are more in that 6-figure hexagon-looking shape. But that's not always the case. Just showing you how these monosaccharides can exist in different forms is all. Even glucose, there's different types of glucose that can exist. Okay, and then we get to the very important topic of disaccharides. And simply put, disaccharides are just two sugars. So we're getting a monosaccharide plus a monosaccharide. Or another way you can say this is a monomer plus another monomer. So once again, a single sugar, a monosaccharide, is a building block or a monomer. And if you put two of these monomers together, you will eventually get your disaccharides. So let's take a look at some of the monosaccharides. Let's look at these equations, or these reactions, if you will, towards the middle of the slide. You can see that glucose plus glucose equals a different type of sugar. It's not glucose times 2. It's something called maltose. And you don't necessarily need to know that, but what you do need to know is how these things are put together. So take a look at glucose plus galactose, which is also a monosaccharide. This equals a different type of disaccharide called lactose. And then when you get an ose and another ose, it makes a different type of ose down here. But if you look at the disaccharides, if you look at maltose, lactose, sucrose, what else is part of this equation or part of this reaction here? And what you should be looking at are the water molecules. So we're coming back to the very important topic of water. Remember, water does a lot of cool things. Helps us with temperature regulation. It helps us with cushioning and lubricants. It also helps us with transportation, but it also helps us with metabolism. So what type of metabolism are we doing here? If I erase this red box and this green arrow, and you can see what the arrow's doing, what we're doing is we're taking one sugar plus one sugar, and we're making a 2 sugar. So 1 plus 1 equals 2. What we're doing is we're building something. We're taking two small substances, and we're making something bigger. So what type of metabolism is that? And hopefully from your chapter 1 notes, you're shouting out anabolism, right? It's an anabolic reaction, meaning we're building. So we go 1 plus 1 equals something bigger than 1. So it's a building reaction. Now, in order to build anything, whether it's sugar, fats, proteins, or all the above, what we have to do is we do have to sacrifice something. We do have to lose something in the process. And what that is water. So, in order for these compounds, in order for these compounds to be stable, they need to be what we call covalently linked. And all that means is this oxygen is kind of holding these two sugars together. And you can see all the different examples. Whether we're talking about sucrose, lactose, maltose, it doesn't matter. They're all kind of holding hands or linked by that oxygen right in the middle, that O. But in order for that O to hold hands and do that, what we needed to do was lose an O and two H's in the process. And in the next few slides, we're going to put some more terminology here, but really what we're doing is we're kind of sucking out a water. We're losing a water in order to build something. And a great analogy I like to use is, I mean, you really can't build anything without losing something, right? If you want to build a house, what do you have to lose? Well, you have to lose a lot of things. If you're building a house, you lose land, right? If you have a 3-acre lot and you're building half an acre house, you're losing half an acre of space on your land for the house. If you are trying to build muscle, you have to sacrifice something. You have to sacrifice a lot of hard work. You have to go to the gym and put in the time. If you're trying to lose weight, you have to sacrifice something. And that's what the human body does on a molecular level every single day, 24/7, is when we're putting these things together, we have to lose something. And what we're losing is this key molecule, water. So let's move on to the next slide and we'll put some terminology to it. So what we just did in regards to that 1 plus 1 equals 2 on the previous slide was this top section of the slide here. It was an anabolic reaction. So I'm going to draw a line splitting these two because these are two different topics here. But you can see, we see the word monomer once again. So we're taking a monomer 1 plus a monomer 2. So 1 plus 1. We have 2 monomers. And what that's eventually going to equal is a 2 monomer or a disaccharide. Now take a look at what's going on here. With the 2 monomers, you have this OH and this OH kind of at the tails of these things. And remember, in order to make these things stable, once we get to the disaccharide, we need that O kind of holding hands or holding these 2 sugars together. So what we have to do is we have to lose all those other parts. So we have to lose an OH and then the other H. And when you put all that stuff together, magically, it equals a water molecule. So in order to build something, in order to go 1 plus 1 equals 2, or 2 plus 1 equals 3, or 10 plus 10 equals 20, we need to lose water. And whenever we lose water from a systemic standpoint, we call that we're dehydrated, right? And that's where we get this name of this type of reaction. This is called a dehydration synthesis reaction. Now let's break that down a little bit. Dehydration means we're losing water, but what does the word synthesis or synthesize mean? And it means to build, right? If I'm synthesizing a pizza, I'm building a pizza. If I'm synthesizing muscle tissue, I'm building muscle tissue. So what we're doing is we are losing a water in order to build something. So this type of reaction, also called a condensation reaction, as you can see in your notes, kind of rare though, we generally call it a dehydration synthesis reaction or just a dehydration reaction. This phrase, this reaction, dehydration synthesis, is the exact same thing as saying an anabolic reaction. It's just a more specific way of saying, hey, we're building something, but in order to build it, we have to lose water. So these two terms in green are synonymous. They're AKAs. They mean the same thing. But what about the flip side? What if we aren't building? What if we're breaking stuff down? What if we broke our arm and we need to break down that old broken bone tissue? What if we're going to the gym and we're actually breaking down muscle tissue because we're working hard? What if we ate that turkey sandwich for lunch and we need to break down the turkey and the bread and the whatever else you put on the turkey sandwich? Well, that's metabolism. We have to build and break. So what we're going to do is we're just going to flip the coin. So if you look down here towards the bottom of the slide, what you see is you see a 2-sugar compound, right? You have monomer 1 and monomer 2, but see how they're holding hands here with the oxygen. So they are combined, they are a disaccharide. And in order to break these things apart, we need to add a water molecule. So to build them, we need to sacrifice water. To break them apart, we need to add water so they're stable when they're by themselves again. So it's just the complete opposite. So we call this a couple different things. What is the complete opposite of anabolism or an anabolic reaction? You already know the name of that. From chapter 1, we called it catabolism or simply a catabolic reaction. And all that means is breaking down. And that's what we're doing, right? We have 2, and then eventually what we're getting is 1 plus 1. So we're separating these things. We're making a big thing into smaller things. The synonymous term with that is called a hydrolysis reaction. So what does this word mean? Hydro means water, and anytime you see lysis, lysis means to cut or to break or to split. And that's exactly what we're doing with this sugar molecule here, where we're splitting it with water. So we add the water in, and what that does is it makes that oxygen break off and go to one of the 2 monomers. We also call this a decomposition reaction, just decomposing, meaning breaking down. But typically speaking, hydrolysis and catabolic reactions are the most common terms. But I'm going to put decomp for decomposition just so you're aware that this word and this word and this word, they all mean the exact same thing. And this is metabolism. This is metabolism in a nutshell. Your body is constantly breaking muscle down, building muscle, building stomach lining cells, killing stomach lining cells. You're making inner cheek cells, the lining of your cheeks in your mouth. When you burn it with hot food, you're building it, you're breaking it. Your nails, sometimes your hair. You build hair and then sometimes it just breaks apart, breaks down, falls out. Skin, you build new skin and then a few weeks later it sheds off of you. We're constantly, no matter what we're talking about, what organ system, constantly building, breaking, building, breaking. All right, and then as we continue to move to so we talked about monosaccharides, we talked about how we make disaccharides and break down disaccharides. Now let's talk about the bigger ones, the polysaccharides. Or if they're really, really poly, if they're really, really big, we can just simply call them, once again, a complex carb. And this is what you typically think when you eat something that's really filling, such as like a potato, a sweet potato, a big bowl of pasta. Just, you don't have to eat too much of it to where it fills you up, it satisfies you. That's where your complex carbs come in. So all it is, though, from a molecular standpoint or a chemical standpoint, is it's just a whole bunch of monomers. It's just a whole bunch of monosaccharides. But if you put 1 monosaccharide plus 1 monosaccharide plus 1 plus 40 plus 20, you kind of get these big, big molecules down here at the bottom. And notice how they're formed and how they're broken down. We form them by an anabolic reaction called dehydration synthesis, and we break them down with decomposition or a catabolic reaction called hydrolysis. That's what we just covered. And then the common examples are starch, glycogen, and cellulose. So real quick, let's talk about these 3 types of complex carbs. We're really only going to spend our time on the middle one, on glycogen, but I do want to introduce what in the world these other 2 are. Starches, you eat a lot of starches. Starches are basically the storage form for plants. So once again, these complex carbs are just a whole bunch of simple sugars put together,
And you can see how the simple sugars are put together in the picture down here. These little tiny circle or rectangle, square, whatever these are, one of them represents a single sugar. And if we just kind of branch them and put them all together in this big long chain, we get these complex carbs or these polysaccharides. So starch is just a whole bunch of simple sugars put together in plants, typically. So when you eat an actual plant, such as a sweet potato or a potato, right, it grows out of the ground, so it is considered a plant. That is a starchy food. If you eat a squash, also it's a vegetable, right? It grows out of the ground, but it's a starchy vegetable. It's a carb. And all it is just a whole bunch of sugars in a plant. Same thing with cellulose. If you look at cellulose down here, very different arrangement. Take a look at how these things are formed or organized. Cellulose really only found in plants as well. This is the stuff that our bodies are really bad at digesting. So like that's the reason why we can't really eat grass. Could you eat grass? Yes, but your body's really not going to break it down really well because we don't have the proper enzymes and hormones to help us break this big molecule up. So we kind of don't eat grass, right? But, you know, lettuce and other vegetables do have a little bit of cellulose in there, but it works as a fiber, so it doesn't, an insoluble fiber, which means it doesn't really get absorbed. It actually ends up leaving our body in a couple days in the toilet bowl. But the big one that I want to highlight is glycogen, because this is the storage form in humans. So plants like to store it as starch and cellulose. Humans store it as this, glycogen. And there are two main locations that I want you to know where we store glycogen. Number one is in your skeletal muscle. So I'll put SK and then M for muscle. And I'm being specific there because there's different types of muscle, right? Your heart muscle is different than your biceps muscle or your abs or your gluteus muscles. Different functions. You also have muscle in your bladder and muscle in your arteries and veins. That's kind of different than doing some push-ups or sit-ups with your skeletal muscles, right? So skeletal muscles are any muscles that are attached to your skeleton. And typically these are the muscles that we like to work out at the gym or wherever we're working out. So that's one location we store this stuff. The second place where we store this in the body is, believe it or not, in your liver. So we love sugar. Once again, brain, red blood cells, love sugar. When you eat, it doesn't matter whether you eat a carrot, an apple, or a big slice of key lime pie, awesome, your body loves that, and it will use that sugar to make energy all over your body, but once again, brain, red blood cells are going to try to hog a lot of it. Now, if we eat too much sugar, no big deal. Sugar's still good, we love it. Our body's going to store it for later because we're constantly moving, right? You think about your 9-to-5 job, or you as a student, all the things that you have to do. Some of you are parents, you got to wrangle the kids and think about how much energy a kid has. We're constantly moving. So if you eat breakfast in the morning, we can only use that sugar so quickly. We're either going to have to store it for later, or we're going to have to get rid of it or turn it as fat. So what we like to do is we like to store it for later. So when I eat a big bowl of oatmeal for breakfast, it gives me energy in the morning, but it's also going to help give me energy later in the afternoon and later that night when I'm exercising or doing whatever I'm doing all day. So when we eat too much sugar, no big deal. We store it inside of your muscles and inside of your liver. So later down the road or the next day, we can have this built-in sugar reserve. And you may have seen this with athletes. Athletes, they have these pasta parties or these big gatherings, big meals the night before a big game or a big match or something, and they eat a whole lot of carbs. And the reason why is because if you eat a whole bunch of carbs for dinner and you wake up for your 8 a.m. race or soccer match or whatever, guess what you're going to have stored in your muscles and in your liver? You're going to have a lot of glycogen. A lot of pent-up energy. So all we have to do is we got to take a couple water molecules and just split these things apart,
And when you split them apart, you have sugar ready to help your muscles and your brain and your red blood cells do their thing. So pretty awesome. Our body loves to store it as glycogen. We want glycogen. That's a good thing. Once again, the problem is why carbs are bad in some circles is if you eat too much sugar, we store it as glycogen. But take a look at where we store glycogen, only in your muscles and liver. You only have so many hundred muscles and your liver is only so big. So once we tap out our glycogen stores and there's no more room, then what does our body do with the sugar? Then we store it as fat. So yes, if you eat oatmeal and then an apple and then a bagel and then another sandwich and then ice cream and then another slice of ice cream or pie later, and you're eating all this sugar throughout the day and then your glycogen is tapped out, yeah, then you will store it as fat. But that goes for anything, any type of macronutrient. So glycogen, storage form of sugar for humans. Our next topic, now that we've covered carbs, is we're going to be moving on to lipids, also known as our oils, also known as our fats. You'll hear me use the term fats more commonly than lipids. Let's discuss a few characteristics that make lipids a little different than carbs and proteins and nucleic acids. So what lipids are, they are chains of hydrocarbons. And remember, the three main ingredients of a lipid is going to be the carbon, hydrogen, oxygen. But the oxygen is kind of rare, if you will. What we're going to have is we're going to have an oxygen here. And then we're just going to have a whole bunch of carbons in this kind of what we call a tail or a chain. And then those carbons are going to have hydrogens linked to them on either side. And I'm not going to draw all the H's in. You'll see it on the next slide. But just to give you an idea, when we see the word hydrocarbons, this is what you're getting at. It's just a whole bunch of carbons attached to even more hydrogens. Now, once again, big important feature of lipids is these things do not really mix well with water. And that means that they are hydrophobic. And hydro refers to water, phobic or phobia means afraid of or strong disliking. So that's going to be really important once again when we talk about the cells. We're actually going to introduce it in a couple of slides with the phospholipids and why these are so important. But it's really going to help us compartmentalize and organize the water all throughout our body. So the monomer for a carbohydrate we called sugars, right? We call them monosaccharides. The monomer for a lipid is what we call fatty acids. And what we're typically going to do is we're going to take a sugar molecule and combine it with 3 fatty acids, and we're going to get something called a triglyceride. And that's kind of how the human body likes to store fat and build fat, is by taking 3 monomers together to form this bigger fat molecule called triglyceride. A triglyceride, excuse me. Now, none of this is going to change in regards to how we form these things. When we're building the fatty acids to form a triglyceride, it's going to be the exact same thing. We're going to lose or sacrifice some water in the process. And if we're going to break apart the fat to release fatty acids, we are going to use water to hydrolyze them, or hydrolysis, break them apart. So nothing in regards to metabolism changes for now. We're also going to talk about phospholipids. Phospholipids are really, really cool things that help us maintain our cell membranes. We're going to discuss steroids and prostaglandins as well on the next few slides. So taking a look at the fatty acids, once again, these are the monomers of our lipids in the human body. You put a whole bunch of fatty acids together, you will get a whole bunch of lipids. Monomers, there we go. And now you can actually see the anatomy. Looking at the picture at the bottom of the screen, you can see this one little O right here, and then the rest of it is just carbon, carbon. Well, actually, there's 2 O's in this fat, and then carbon, 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 and then it's attached to several hydrogens. So where we get this hydrophobic part is all of these hydrogens and carbons. This hydrocarbon chain is the part that really doesn't mix well with water. And the part that does mix well with water, this hydroxyl group, or what we just simply call OH, this is called the hydrophilic region. And once again, hydro means water, philic or philia means to love or a strong attraction to. And that kind of makes sense if you think about the chemical makeup of it. Look at water. Water is H2O, and look at this structure. This is HO. So by just adding a simple another hydrogen, you're getting water. So these things very, very friendly with water, no big deal. But the majority, as you can see, let's call this 80% of the fatty acid, is very hydrophobic. It's a strong disliking towards water. And I'm sure you've heard of the two different types of fatty acids, just going through middle school, high school, health class, that kind of thing. You've heard of saturated fats and unsaturated fats. Saturated fats, typically the rule is they are solid at room temperature. So this is mainly your animal fats. After you fry or grill a burger or chicken or steak on the pan or grill or something, that fat that's left over kind of congeals or solidifies. That's a saturated fat. And then unsaturated fat is typically liquid at room temperature, and this is a lot of your oils. This is your olive oil, your vegetable oil, your peanut oil, your sunflower oil, whatever oils you cook with or use. Now, both of them are healthy. I mean, generally you want a lot more unsaturated fats compared to saturated. You don't want to eat too much animal fat, according to research and FDA and CDC and all those people. But too much of unsaturated fat is still fat. Even the omega-3s that have been really popular the last few years with heart health and eye health and brain health, if you eat too many omega-3s, it is fatty and it can cause some health issues. It actually leads to increased chances of heart attack. So you kind of want a balance. You don't want too much of anything, and even water. You don't want too much of water in your body, right? So here's showing you the difference between the saturated and unsaturated fats. As I mentioned, one's solid at room temperature, one's liquid at room temperature. But if you look at the actual chemical makeup of them, they're pretty similar. The only difference that you'll see is with the unsaturated bond, you have this kind of double bond where we're missing a normal C by itself connecting the hydrogens, and that causes kind of a kink in the chain. And depending on what carbon, what letter, or what number that carbon is at, that determines what type of fat it is. So we get omega-3s and omega-6s and omega-9s. It's just those are labeled by where the kink is in the chain. So once again, the way our body stores fats is in triplets or trios and threes. So what we do is we take a glycerol molecule, which is a sugar, and you can see the chemical makeup of what glycerol looks like right there. It's just a bunch of carbon, hydrogen, and oxygen, just like sugars, right? And what we're going to do is we're going to combine them. The key number is 3 with fatty acids, with fats. So we're going to combine 3 of those monomers, 3 fatty acids, and we eventually are going to get our storage form called the triglyceride. So when you have belly fat, when you have fat around your heart and your kidneys, just any type of fat, the fat in your eyeballs or behind your eyeballs, that is in the form of triglycerides. Now, as I mentioned, there's no change in regards to metabolism. If you take a look, when we're putting these 3 fatty acids together and we're combining it with the glycerol molecule, we are losing a water. We are losing a water. We are losing a water. So if you look at the end equation, what we did was we put this whole big thing together. 1 plus 1 plus 1 plus 1 equals the 3 fatty acids and the glycerol, but we lost 3 waters because we had to add the 3 fatty acids. It's the same thing when we break this down. If we want to break down the fat to release fatty acids, say that we're on the ketone diet and we're not eating sugar and we need to use fat for energy, or we're just on a really, really long hike and we don't have food readily available to us, we will do the exact opposite. Just like we saw in the carbs, we're going to use those 3 water molecules to break apart these bonds. And once again, we call that hydrolysis. Now, fat's got a lot of cool purposes. It can serve as protection. One of the big functions that you need to know is it's an energy reserve in the body. It is not the preferred fuel source. It is not the easiest fuel source. Remember, that is sugar. Your body loves sugar. Brain, red blood cells thrive on sugar. But if we are running low on sugar and we're tapped out on all that glycogen that we stored, we will start to break down fats. That's the next domino in the domino effect, or the snowball effect. So this is an energy reserve. So when I skip lunch because I'm too busy recording a lecture and I haven't eaten in several hours, fat being broken down is what's keeping me going. So I don't pass out, so I don't have low energy levels, so I can keep doing what I need to do. But it is not the preferred fuel source. It's just a backup supply. It's an emergency supply. Phospholipids are another form of how we make fats, or if you will, store fats in the body. Big difference with a phospholipid is we're only going to have two fatty acids. So once again, a triglyceride is our storage form of fat. The fat on your belly, the fat on the back of your arms, the fat in your eyeball, the fat protecting and warming up your organs is in the form of triglycerides. A phospholipid, what this is going to do is this is going to make the outside of our cells. And what we call that is a cell membrane. So remember, with chapter 1, very important, we have to compartmentalize everything. We have to separate environments. We have to have an outside and an inside. And that's not just with your organs. That's not just with your tissues. It's actually with the billions and billions of cells in your body too. They all need their own little space, their own little apartment. So how we do that is we put a whole bunch of fat on the outside of the cell. So once again, the main stuff floating inside the cell is water. The main stuff floating around the cell, outside the cell, is water. So we have to separate these two water components to make sure our cells don't flood or that we don't run low on water and dehydrate and shrivel up. And how we do that is we introduce a whole lot of fat to the outside of the cell. Once again, water doesn't mix well with fat. So as you can see with the second bullet point, they arrange themselves, these phospholipids, so that the hydrophilic part, the phosphate head or the phosphate group, that's why they get the name phospholipid, this actually faces out towards the water. So whether it's the outside of the cell, let's look at this picture right here. Let's just draw a little wall. Here's the outside of the cell. So this would be the outside water compartment. This would be the inside water component. These little red circular heads are the phosphate groups, or the phosphorus areas, and they are hydrophilic. They don't mind water. They like water. So therefore, they are going to be actually swimming towards the water or touching the water. They don't have a problem with water. But remember, the fatty acid chains, the tails with all those carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, that's the hydrophobic part. And notice how they're oriented. They're actually oriented facing each other inside of this kind of wall cell membrane. And what that creates is this fatty barrier. And what that does is it avoids water from getting in and out of the cell willy-nilly, right? Just free, let's just move water back and forth however we please. No, there actually is a process to it. And this fat chain or this fat wall is blocking that. So what we call this, we're going to introduce this more in detail in chapter 3 when we actually talk about the cells, but what we call this is a phospholipid bilayer, because there's actually two layers of these fatty acid tails, or tail-looking structures. So we have one layer where the heads are facing towards the outside of the cell, and then we have another layer where the heads are facing towards the inside of the cell. So since it's two layers, we call this a bilayer, as you can see here. Other types of lipids are steroids And you can see by looking at the picture, steroids are built a little differently. They don't exactly have those long fatty acid chains, those hydrocarbons. And then they definitely don't have them in groups of 3 like the triglycerides, right? So they are built a little differently. They kind of form these rings instead of the tails or the chains. And we're going to be talking about a few steroids next semester, but we're really only going to mention one for Anatomy and Physiology 1, and that is this one, cholesterol. And as you can see, it's the most abundant and important steroid in the body, so it makes sense that we're going to talk about it this semester, and then we'll introduce kind of the smaller steroids later on in the curriculum. So cholesterol, very, very important. This also, similar to carbs in our society, gets a bad rap, right? Oh, my cholesterol's too high. I can't eat this food. Stay away from eggs because it'll raise your cholesterol. Yes, it can if you have high cholesterol, and sometimes that's a genetic issue, unfortunately. But if you don't have any cholesterol, that can be even more detrimental. That can be even worse than having too much cholesterol. So just like pretty much everything we've talked about so far this semester, balance is a necessity, homeostasis. We don't want too much of this, but we also don't want too little of it. We kind of need this nice, happy middle ground. And cholesterol is no different. So you can see all the awesome uses for cholesterol: building hormones, your sex hormones such as testosterone, estrogen, progesterone. Those are all steroid based. Without cholesterol, you can't build those sex hormones. So another reason to have fat in your diet, so you can have the proper sex hormones and good hormone chemistry. Cortisol is considered a steroid as well. Stress hormone, we'll talk about that next semester. But they also work as signaling molecules. They can help with cell-to-cell and tissue-to-tissue communication. And the big thing that we're going to spend a lot of time on with cholesterol specifically is this is a huge component of the cell membrane, stabilizing the cell membrane, making sure that those phospholipids are intact, are healthy. So we'll talk more about cholesterol next chapter when we actually get to the cell membrane. And then the last example of a lipid are prostaglandins, and these things are nuts. They are complicated, to say the least. As you can see in your notes, a couple things that prostaglandins do. They are signaling molecules. They're built from unsaturated fatty acids, so their ingredients are the same as our triglycerides, our steroids, those kind of things, our phospholipids. But we named 3 things that these prostaglandins do. As you can see, they regulate inflammation. They help your nerves get used to or adapt to pain. And they create smooth muscle contractions. Yes, but they do like 19 million other things as well. Just to give you an idea of some of these things that they also do, they're big vasodilators. They make sure that platelets, those clotting guys that we talked about, they don't get in groups and hang out, because that can form random clots in our body. And if we get random clots formed in our body, they can go to wrong places, such as our lungs or our brain, and that can be deadly. These help induce labor with the baby making process. They make sure that the pressure of your eyeball is intact in regards to inflammation, as you can see. So a lot of things with inflammation, big part of the immune response, but it's also just homeostasis, making sure your eye doesn't blow up or you fall apart. Regulates hormones, regulates cell growth. We're going to talk about how the cell actually grows and divides, and you really can't have any of this without prostaglandins, without fats. A big part of, we talked about sweating and shivering. Prostaglandins are involved with talking to that special part of the brain that helps with this. Also in severe sweating, such as if we're running or inducing a fever in order to cook a virus or something like that, that also has to deal with inflammation. So if we detect a virus in the body, we will tell the brain to, hey, start elevating the body temperature so we can kill this virus. I'm trying to think of other things. I'm kind of blanking. I'm not really doing it justice. helps with kidney filtration. A lot of crazy cool things. As you advance in your studies and you learn about the immune system, we'll talk a little bit about them in smooth muscle with the digestive system, but these things are very multifaceted, very cool. But the big thing we want you to get is that they are made up of fatty acids. That's the building block. So fats, yes, are important for your cells. They're important for energy storage. They're important for hormones, but they're also important for all of that stuff I just mentioned, mainly inflammation. All right, so we knocked out carbs, we knocked out lipids, so we have two more macromolecules to go. Proteins and nucleic acids are remaining. Let me just take a quick second to just kind of recap all this. Remember, the four major macromolecules are carbs, lipids, proteins, nucleic acids, and all of them have the four, or at least three, major elements in your body. All of them are made up of carbon, hydrogen, oxygen. And these last two that we're going to introduce are going to have that fourth ingredient, or that fourth element, nitrogen. So proteins, nucleic acids, a little bit different. Okay, so first thing that is unique about proteins is we have a different monomer. So let's go back and reflect on the monomers we've talked about so far. Carbohydrates are built from the monosaccharides, right? The monomer of a carb is a monosaccharide, or a sugar, a one sugar, if you will. The monomers of lipids are fatty acids, and the monomers of proteins are called amino acids. You put a whole bunch of amino acids together, you will eventually form a protein. Now, these amino acids are linked by bonds, just like our carbs and our lipids were, and they are formed with dehydration synthesis, just like we've talked about, and they're broken by hydrolysis, just like we've talked about. Nothing changes there. So we'll show you those bonds in a few slides, but in regards to how we build and break these things, it's all the same. As I mentioned on the previous slide, big difference, you see our CHON, C-H-O, and then the N is the very unique part, different than carbs and fats. We are now introducing nitrogen into the macromolecules here for the first time in proteins. And this will be very important later next semester, how we process proteins in regards to the liver and kidneys and all that. We also have some sulfur and phosphorus as well, but nitrogen being the main difference. Now, proteins are going to fold using different procedures or different steps, as you can see. And remember from chapter 1, the most important thing of this, possibly this entire class, is structure complements function, or shape complements function. So the shape of a protein dictates what the protein actually does. So what we're going to talk about in about 6 or 7 slides is we have a primary stage where we line all the amino acids up. Then we're going to start the folding, complete the folding, and then combine it with other folded things. And that exact weird folded shape determines exactly what that protein does. Because insulin is very different than, let's say, angiotensin or pepsin. They're all proteins, but they work very differently. So we'll discuss that more in just a little bit. But before we talk about the folding, let's talk about the many functions of what proteins can do. As you can see on this slide, there are 6 big things that proteins do, but similar to those prostaglandins, there's a lot more than 6. We're just covering some of the big basics. And the first one, in no particular order, is transportation. So if you look at this picture, what we see is that phospholipid bilayer, which is the cell membrane or the outside of a cell. So here you have what we call the extracellular space, or the interstitial space, which is known as the outside of the cell. And this would be the intracellular space, or the inside of the cell. And you can see we have all these little weird green looking things going in and out all over the place, and how they get in and out, sometimes things mix well with fat and they can just go right through that fat barrier, no big deal. But if something is water-based or made up of water, remember water and fat don't mix very well. So therefore, how are we going to get things in and out of the cell if they don't mix well with the fat? And one of the ways we do that is with proteins. And you can see these proteins that are embedded in the cell membrane. I'm currently circling them in red. These are kind of like these detour routes or these magical secret bookshelf kind of things, like when you pull a book and then the whole thing revolves to the other side and reveals something weird. That's kind of what these things do. So some of them actually change shape, and like you can see for this second one right here that I drew an arrow to, something can actually bind to the protein, and then it, like that bookcase that I mentioned, it will actually open up on this end and spit the contents out into the cell. Sometimes they're just big bridges that allow stuff to go in and out, no problem. And sometimes they need a little extra help. Sometimes they need a little energy, and we'll talk about the energy molecule in just a moment. But we have to get things in and out of the cell to maintain homeostasis, and proteins is one of those ways that we accomplish that. Several proteins in the body function as hormones, and a hormone is a specific chemical that's floating in the bloodstream, and it affects another part of the body. So for example, growth hormone is a hormone that you may have heard of, and when it's released from a specific part of the brain, it goes all over the body and it tells your body to grow. Yeah, you guessed it. So it actually targets muscle cells and bone cells and organ cells to grow and get bigger. And a lot of your growth hormone is obviously released during childhood and puberty, right? But we still release a little bit as adults as well to repair tissues. Other examples, as you can see here, are insulin and glucagon. These are two hormones that are constantly traveling through your bloodstream. They're monitored, controlled by the pancreas. Also, the liver plays a little role in this. And they are responsible for maintaining your blood sugar homeostasis, making sure that we don't get hyperglycemic or hypoglycemic. So not all hormones are proteins, but a good amount of them are actual just proteins. And all that means is they're just made up of a bunch of those monomers, those amino acids. Another neat feature of proteins is they serve as enzymes. And enzymes are really cool things. What they do is they work as a catalyst to a chemical reaction. So all of those metabolic activities, those building and breaking down, anabolic, catabolic, enzymes can just make things happen faster. And a perfect example of an enzyme is lactase, because most of us have heard of the sugar in milk, yogurt, cheese, kind of dairy products, lactose. Right? Some of us listening to this video may even be lactose intolerant, unfortunately. So lactase is an enzyme that helps you break down lactose, the sugar. So thankfully, fortunately, I am not lactose intolerant, and I'm sorry for anybody who is. And actually, long term, you might be healthier. That milk, yogurt, cheese aren't always the healthiest food options, so you may or may not be missing out. But take somebody like me who is not lactose intolerant. I eat a piece of cheese, no big deal. And the reason why is because when I eat that cheese, when it hits my stomach, I have this enzyme that helps break it down very, very quickly. So then it eventually goes into my small intestine, broken down just like my carbs and fats and proteins and everything else that I eat on a normal, everyday basis. Somebody who does not have this enzyme, who is lactose intolerant or doesn't have a lot of the lactase enzyme, what happens is you eat that milk, yogurt, cheese product, and your body has a hard time breaking it down. So take some yogurt or take a glass of milk and leave it outside on a very hot summer day. Because it's essentially what you're doing is when you're eating food, right? Inside of our bodies, 98.6 degrees, maybe a little warmer. Picture taking a little tub of yogurt or a piece of cheese and putting it out on the sidewalk on a 99-degree day in the summer. What's going to happen after a few hours is that's going to get really gross, really nasty, right? If you don't break it down. So if you don't have this enzyme, that's going to start causing some chemical reactions, and you're going to get some bloated and gassy like symptoms like folks who with lactose intolerant get, unfortunately. So I use this as an example. An enzyme is just something that makes a reaction happen faster. Your body will eventually break that down. But folks who don't have lactose intolerance, they just break it down very efficiently, very quickly, so they can eat more milk, yogurt, cheese, no big deal. So enzyme just speeds things up. Other functions of proteins is these are the main building blocks of your body. We are going to spend a long time talking about specifically collagen proteins, as you can see in this picture, but we'll also spend a little bit of time talking about elastin proteins, really stretchy, flexible proteins in our body. We'll talk about keratin in our skin, our hair, and nails. That's a strong protein. But the majority of your body, a good part of it is made up of protein, and a lot of it is because you have so much muscle, right? We have over 600 muscles in the body, and a lot of your muscle tissue is made up of protein, and a lot of your tendons and ligaments that help with those muscles and those joints are made up of this stuff, collagen. So very, very strong stuff. Make sure that these things don't rip apart and that they can maintain their integrity. An additional function of proteins, they act as buffers. And we haven't introduced pH yet. We're going to get into that more so next semester. But what a buffer is it kind of just evens things out. It kind of just takes one of an extreme on either side and kind of just brings it closer towards a happy medium. And a lot of these happen actually inside of your cells. We're going to talk about this specifically with red blood cells next semester. But we can make sure that our body is not too acidic or too alkaline based on the proteins inside of our cells floating around, also inside of our fluids outside the cells. So we will discuss this in more detail, but not until next semester. And then finally, we get to the immunity function of proteins, and we're really going to cover this next semester as well, also in your microbiology class in the future. But a lot of your immune responses have to deal with how our cells recognize things and talk to each other, and also how our body creates defense mechanisms against foreign things. So we make things such as antigens and antibodies. I'm sure you've heard of antibodies. Whenever you, for example, get the flu, your body will hopefully make antibodies against that flu so you don't get that same flu 3 months later, right? Generally, if you get the flu, you only get it once a year or once every several years. You don't get it over and over and over again because that would mean your immune system wouldn't be working properly. So you make these antibodies, which are kind of these remember cells, if you will, your memory cells, and they help your body fight against any future exposures. But like I mentioned, we'll get more into that in Anatomy and Physiology 2 next semester. All right, so going back to the monomers of proteins, once again, they are called amino acids. And they are going to have a little different structure compared to our monomers found in carbs and lipids. And the big difference, once again, is the nitrogen. The nitrogen is unique to just proteins, and we're also going to have them in nucleic acids in just a little bit. But as you can see, the structure of the amino acids, we have something called an amino group or an amine group, and on the left side, and all that is a nitrogen connected to a couple hydrogens. We have a carboxyl group, which we also can see in fats, and we saw a C and then this OOH. And then you have a central carbon connected to a hydrogen and connected to this kind of R looking thing, or this variable. And in our body, in the human body, there are 20 different amino acids, and they're all the same in regards to the amine group, the central carbon, and the carboxyl group. The only difference between all 20 amino acids in the body is this variable group, or what we call this side chain, this R group. So You probably haven't heard of too many of these unless you're like a big bodybuilder, weightlifter kind of person. But a very popular amino acid you may have heard of is tryptophan. Tryptophan, very common food talk during Thanksgiving. Has sleeping properties to it, and if you eat too much turkey, people say, "Oh, I had too much tryptophan, I'm tired." You'd have to eat a lot of turkey for tryptophan to actually have that kind of effect. There's other reasons why you're tired on Thanksgiving. We can talk about on another day. But tryptophan is an amino acid where we have this nitrogen, two hydrogens, central carbon, carboxyl group, and then it's got a specific R group. And it's different from all the other 19 amino acids. And they all have their own kind of unique thing to them. But once again, big picture, you put a whole bunch of these amino acids together, you're eventually going to get our proteins. So just in case you're wondering, what are the other names of the 19 amino acids other than tryptophan? Here they are, really small, but glutamine, valine, leucine, isoleucine, aspartate, asparagine, phenylalanine, are a couple off the top of my head. I used to know them all. I don't anymore. But if you take a look at their actual structure, the pink stuff, the R groups, that's what makes them all different. For the most part, everything else is kind of the same. And these 20 amino acids grouped in different variable orders is what's going to dictate what kind of protein we have. So for example, are we going to make an antibody protein? Are we going to make an enzyme protein? Are we going to make a transport protein? Are we going to make a hormone protein? Well, that is dictated or determined by the order and how many of these 20 different amino acids we use. So we'll talk more about that as well. Okay, amino acids are held together by something called peptide bonds, and really, y'all, it's the exact same thing as the carbohydrates and the lipids. We're still, if you look at the picture, we're still using water. We're still going to sacrifice water, suck it out in a dehydration synthesis reaction, and in order to break that apart later down the road, we're going to use water to break it apart in the hydrolysis reaction. The reason why it's got a special name, as in peptide bond, is because of the special element. That nitrogen is very, very unique, once again, to proteins and amino acids. We don't have this in carbs and in lipids. So because we have this amine group binding with that carboxyl group, we have a special name. We call them peptide bonds. And if you put, once again, you put a whole bunch of peptide bonds together, you eventually will form a protein. Okay, so we mentioned earlier about folding and how the shape is going to determine the function. And we talked about the 4 steps to them. Now we're actually just going to be more detailed and actually go into depth on what is happening during these 4 steps. And the 4 steps are easy to remember because basically they're just numbered. You can see number 1 is primary, 2 would be secondary, the 3rd step is tertiary, and then the 4th step, the final step, is quaternary. So what we're going to be doing from the primary standpoint is we're going to start really, really basic, and then we're going to get a little more complex in secondary and more complex in the last 2. So here's what you need to know for the primary sequence. All we're doing in the primary sequence is lining up these amino acids. We're just putting them in the right order. So if you go back to that chart with all the 20 different ones, if we have 2 tryptophans and then a glutamine, that is a very, very different protein versus if we have a tryptophan and then a glutamine and then another glutamine instead of 2 tryptophans. Completely different structure, and we're eventually going to have a completely different function. So what we're doing in the primary sequence is we're just ordering. And as you can, just like a grocery list, it's actually a really good example, just like a list. So maybe our tryptophan is number 1 and number 5, and then we'll have a valine at number 8 and an isoleucine at number 9. You don't have to know the names of these amino acids by any means. You're not going to get tested on them. I'm just telling you some examples of them to kind of make it a little more real for you so you understand what we're actually doing during this process. So primary, we're just putting things in order, just lining it all up. Let's move on to secondary on the next slide. With secondary, the big key thing that we're doing is we are starting the folding process. So once again, our bodies are 3D, our organs, tissues are three-dimensional, our cells and the things inside of our cells are three-dimensional even though they're really small. So we are going to fold this into a three-dimensional shape, and the folding begins right here in the secondary stage. Now, the results of folding, there are different shapes that we can have, but there really are two main ones. And you can see them in the pictures. The first one, in no particular order, is something called a beta pleated sheet. And I'm not really a furniture decor kind of guy, but there's certain blinds and like curtains that kind of bend this way. If you take a paper and you're like folding it for like a letter, put it in an envelope, you can kind of see where I'm getting at here. So we're taking those 11 or 12 amino acids that we organized in the primary sequence, primary stage, and now all we're doing is we're just putting them together and folding them, because eventually we're going to get this really cool folded protein. So a beta pleated sheet is one way we can do it. A second way we can do it is something called an alpha helix, and this one you might be a little bit more familiar with, kind of like a corkscrew kind of looking shape. If you've ever been on a roller coaster or something like that, you'll kind of get this spiraling looking shape to it. So most proteins start out this way. They're lined up, and then they either kind of fold like these, like this envelope, this folded piece of paper, the beta plated sheet, or they fold in this kind of spirally corkscrew looking structure called the alpha helix. In the secondary structure, we just started the folding, and the tertiary structure, we're ending the folding. Now, believe it or not, I know that we have a fourth stage, we still have the quaternary stage, but the tertiary structure is actually a complete protein, as long as it has enough amino acids to it technically, but this is the end of the folding stage. So this can serve as a functional protein, and a lot of proteins are kind of in this stage. They just kind of stop here, and that's what they do. They are functional, they do work. A lot of our fibrous proteins exist in this state. And all it is, I mean, it looks like a mess here, right? But really all it is either those alpha helices or those beta plated sheets just kind of all folded together and all sorts of different directions. So we are stopping the folding process here. This actually is a complete protein, and it's ready to do its job, whether it's a hormone or an antibody or an enzyme, it doesn't matter. It can serve its purpose. But let's move on to the quaternary structure, and I'll show you what the difference is between those two. And the difference is the quaternary structure is simply a whole bunch of tertiary structures put together is all. So once again, a tertiary structure is a complete protein. It's a functional protein. It can do its job, or a job. But a quaternary structure is just a really big protein. And all we're doing is we're just putting the tertiaries together, multiple tertiaries together. So in this picture, what you're seeing is you can actually see 4 tertiaries put together. If you take a look at these little purple frisbee looking things, and then you can kind of separate it. So that would be 1 tertiary folding, that would be 2, sorry, that would be 3, and then this would be a 4th one. So what we have is a complete protein here, but it's really 4 separate proteins all kind of combined and glued together to make this big protein. And this is going to be a really important word next semester, really important term, hemoglobin. We're going to spend a long time talking about the importance of it. It's really an awesome protein. So I love this slide because it kind of puts the last 4 or 5 slides and all that information into one big summary. Really great picture. Once again, primary, all we're doing is we're just lining things up, putting things in the proper order, so then we can eventually begin to fold them in the secondary stage. And once again, we can get that alpha helix corkscrew looking thing, or we can kind of get that envelope or beta plated sheet looking thing. Then, once we're done folding, we actually have a functional protein in the tertiary stage. And if you put a whole bunch of tertiaries together, you can get the bigger proteins called the quaternary stage. So take a little time to review this. This will help you making sure you got it all straightened out in your head. We've covered carbs, we've covered lipids, we've covered proteins. The last macromolecule for this chapter are the nucleic acids. So let's get rolling. With the nucleic acids, we are going to see all four major elements of the body. So we're going to see some carbon, we're going to see some hydrogen, we're going to see some oxygen, and then we're going to have our own unique nitrogen base similar to our amino acids. So we have a nitrogen base, we also have a sugar. So you can see the CHO, a lot of that CHO is going to be found in this sugar. And then we have a phosphate group, such as what we saw on the phospholipid bilayer, right, with the fatty acids. So you put those three things together. You have a nitrogen base, and we're going to have 5 nitrogen bases I'm going to introduce on the next slide. You have a sugar, and you have a phosphate group, and you get what we call nucleotides or nucleic acids. So there are 3 types. There's actually really 2 types of nucleic acids, true nucleic acids. Little adjustment here. The 2 types of nucleic acids are your DNA and RNA. DNA stands for deoxyribonucleic acid, and RNA stands for ribonucleic acid. And then we have ATP. ATP stands for adenosine triphosphate. We're going to have some slides on all 3 of these. But ATP is not technically a nucleic acid, but it does have the 3 parts of a nucleic acid. But it's not called adenosine triphosphate nucleic acid. It's just adenosine triphosphate. So it's basically just the ingredients. So they're all going to be unique in regards to their function because they're all different, right? Even though they have the same ingredients, some are going to have different shaped sugars, some are going to have different nitrogenous bases, and or some are going to have different phosphate groups, different amounts of phosphate groups. And because the shape's going to be different, as we know by now, the function is going to be different for all 3 of these. So here are the 5 nitrogenous bases that I mentioned. And if you take a look at them, they all kind of have this hexagon-looking shape to them. On the bottom, you'll see a hexagon attached to a pentagon-looking shape. But the key thing that is common in all of them is you have a nitrogen somewhere in there, in this kind of central ring. And as you can see in guanine, you have a whole bunch of nitrogens, and then adenine has a few as well. So, let's talk about these nitrogenous bases. These things, in regards to DNA and RNA, they like to pair together. They like to pair with each other. And they're very, very, very picky. Basically, they kind of have their best friend or let's say their spouse, and they don't hang out with other spouses. They don't hang out with other people. So the relationships is as follows. In DNA, your adenine, which we abbreviate as A, you don't need to know the actual names. It will help you, but all you would need to know is A for adenine, C for cytosine, G for guanine, etc. A is always, always, always best friends with T. So adenine and thymine are married, or let's say they're 2 dogs that grew up together. They're 2 puppies, and they were raised together, and now they're inseparable. They just go everywhere with each other. They can't be separated. A and T are always together. The other happy couple in DNA is cytosine is always paired with guanine. And those are the 4 nitrogenous bases of DNA. So wherever you have an A, and I'll show you an example of this in just a moment, wherever you have an A, there's going to be a T on the other end. Whenever you have a T, there's going to be an A on the other end. And then same thing goes for the C and G. Now when this gets flip-flopped, if an A is paired with a G, or if a C is paired with a T, that's where we have issues. That's where we have mutations, and if you have enough of them, that's what we call cancer. It's just mutations in the cell's genetic material. So we don't want that. We always want A to be best friends with T and C to be best friends with G. That's what we have in healthy cells. Let's look at RNA. RNA has a similar setup. C and G are the same, nothing changes. So cytosine is always best friends with guanine, and vice versa. Guanine always best friends with cytosine. But there is no thymine. There is no T in RNA. So A has to find a new best friend, and the C and G are always together. They're already paired, so we can't bug them. So we have a substitute, and the substitute is this U, this uracil. So that's the big difference. If you notice what we just wrote up here, what we drew, is C and G are the same. The difference is what A pairs with. We have T for thymine in DNA. We have U, or uracil, in RNA. And that's the major difference I want you to know. We'll talk about a few other more subtle differences, but that's the biggest thing. So there are 5 nitrogenous bases in our body, and both of these nucleic acids, DNA and RNA, have 4 of the 5. And A, C, and G are found in both. The only difference is that T and the U. So first let's dive into DNA, deoxyribonucleic acid. Deoxyribonucleic acid is basically your genetic material. It's what makes you you. It's what gives you your hair color, your eye color, your traits. Basically whatever mom and dad or your grandparents gave you, that's you. You're just a combination. You're just a big mush hybrid of your mom and dad, and they were mush hybrids of their mom and dad and your grandparents and great grandparents and so forth. But this is who you are. The reason why I'm not 6'8" is because my dad is 5'11" and my mom is 5'4". So there are those weird exceptions, but unfortunately my parents aren't tall, my grandparents weren't tall, so I'm not really that tall. And, it just kind of happens that way. My dad has brown hair, my mom has brown hair, I have 2 brothers, and myself, we all have brown hair. That's in our genes, that's in our DNA, that's what we have been given. So, once again, our DNA has a code. A is always best friends with T, and the C is always best friends with G. And if you take the time to actually look at this picture here on the right, you'll see that it's always the case. They have a red for adenine and a yellow, yeah, I guess it's yellow, for thymine, and they're always together. Whenever you see a red stick, it's paired with a yellow stick. Yellow stick paired with a red. Yellow, red, red, yellow, and that never differs. And then you have the 2 other ones, CG, blue, green, they're always together. You have blue, green, green, blue, green, blue, green, blue. And once again, as long as AT and CG are together, and we're not mixing those up in the wrong combination, the cell pretty much should be healthy. We shouldn't have any cancer-like issues. So another unique thing with DNA is it forms this cool 3D shape, and we actually didn't know this until like the we didn't know this, the public didn't know this until like the 1950s, 1960s really, but the scientists who discovered this were Rosalind Franklin. She really discovered it probably in the late 40s, early 50s, so it's still kind of new to us. It's not, less than 100 years. But it kind of creates this alpha helix, if you will, that double helix that we saw, this kind of spiraling looking thing. But the difference is we're just going to have 2 of them, so we call it a double helix.
So we kind of get this multiple corkscrew looking appearance. And that's how your DNA is smushed into the nuclear or the brain material of your cells. So it actually is what we call double-stranded. The A is always best friends with the T. So A's on one strand and T's on the other. And then G is always on one strand and C is on the other. And once again, this slide is just showing you how they interact with one another. A, always best friends with T, good to go. G, always best friends with C. That's what we want to see, DNA, AT, GC.
Now with RNA, there are a couple differences. We already pointed out one, the big one being that there is no thymine. The U for uracil substitutes for the thymine. So C and G are still best friends, but A is now best friends with U. And the other big difference that I want you to notice is that there is no double-stranded structure. There is no double helix. What we have here is a single strand, A helix, 1. Because what we're doing is we're actually, believe it or not, we're going to get into more detail next chapter and show you how this works, but we're actually making RNA from our DNA. So we're actually going to split the DNA temporarily, and we're going to use one of those chains or one of those sides of the DNA and pair it and make an RNA structure, an RNA molecule. And what that's going to do is eventually help us make protein. So this bottom bullet really sums up what I just said. We're going to actually take our RNA from our DNA, from our genetic code, and then we're going to use the RNA to eventually make a protein. Total mind blow there, right? Whoa. We just talked about proteins. Proteins are just a bunch of amino acids. What the heck are you doing here? We're mixing nucleic acids with amino acids. That's confusing. Yeah, kinda. Remember that primary stage with amino acids, right? That primary stage, we're putting them in order. Well, something has to tell us what order this stuff goes in. So we need a blueprint, we need a map, we need a guidance counselor to show us what goes before what. Where does the tryptophan go? Does it go at the front of the line, or the end of the line, or the middle of the line? And what tells us is the RNA. The RNA is a code that tells us the order of our amino acids. And once again, the order of the amino acids is going to make different shapes. If you mix up the order, you're going to have a different shape. If you have a different shape, you have a different function. So we take our DNA, make an RNA for the code, and then the RNA is eventually going to code for a protein, which is going to be really cool when we bring it full circle in chapter 3 before your first test. We're going to have all the cell stuff put together, and you're going to know so much cool information. It's going to be really exciting for you. It's exciting for me. So it'll be exciting for you too, I hope. So a couple differences between DNA and RNA. Take a look at the pictures before we actually show you the black and white words. DNA, once again, double-stranded. RNA is single-stranded. Trying to show it to you here. We'll highlight it in black. It's a single-stranded thing, but what we're getting is, or how we're making it, is we're stealing it from the DNA, if you will. We're actually splitting the DNA, and we're copying the code from the DNA. All those ATs and CGs, we're going to use that, and then we're going to turn it into our ACGs and Us. Because here's the thing. The little tiny guys inside of your cells that make proteins, they speak a certain language. And that certain language is ACG and U. They don't know what in the world a T is. If you tell a little protein maker, make this, and the code is CTTAAGT, they're going to freak out and have no idea what's going on. The whole thing's going to self-destruct. We're going to have a huge issue on our hands. But if you tell the little protein maker, here's the code ACUUGAU, oh yeah, no problem, I know what that is, and then they spit the protein out, no big deal. So we need to change it to the language that the protein makers speak, and that's the RNA with that U. Big difference. So once again, DNA double-stranded, RNA single-stranded. DNA is going to be found inside the nucleus of the cell. We're going to highlight this more when we talk about what a nucleus is and all the different parts of the cell. So don't really worry or stress out about that too much. We're going to introduce that. DNA is found in the nucleus. RNA is also, it's going to be created in the nucleus, but we're going to eventually, or pretty much immediately, spit it out of the nucleus into something called the cytoplasm. And that's where the little protein guys, the protein makers, are going to be found. The sugar is something called deoxyribose. I'll show you a picture in just a moment showing you the subtle difference between sugar deoxyribose and the sugar ribose. And then that's probably the most important is the bases, the nitrogenous bases, or what we call the nucleotides. ACGT for DNA, A and T are always best friends. And then ACGU for RNA, A and U are always best friends. And then why do we have all this? DNA is what makes you you. It makes you completely unique. Even if you have brothers and sisters, unless you're identical twins, you're very different because you didn't get the exact same gene pool from your mom and dad. There's a lot of cells in your mom and dad and a lot of different genes, and depending on when you were conceived, you got different genes. So even though you may look alike, talk alike, you are very different in regards to your genes. You're more similar than non-siblings, but you are different. And then our RNA, we're going to use our DNA to make proteins. We're going to get that code and give the code to the proteins so we can make all those cool enzymes and hormones and antibodies and building blocks and muscle fibers and tissues, tendons, ligaments, all the cool things that proteins can do. It all starts here with the DNA and the RNA. Finally, let's talk about ATP, or adenosine triphosphate. I'm going to show you on the next slide the subtle difference between DNA and RNA to close out the chapter. But before that, I want to discuss ATP. You are probably going to be very tired and sick and tired of me saying ATP, but this is so important. Excuse me. Everything that you do, it uses ATP. If you look at this bottom bullet point, this is what sums it up. Used for energy in the body. This is the energy in the body. This is the energy currency. If you and I, we go to the grocery store and buy a bottle of water or a candy bar or whatever we're buying, I don't know, deodorant, whatever, we use US dollars, right? That's our currency. So we're either going to take out quarters and pennies or paper bills, or we're going to pay with a debit or credit card or something like that, or a checkbook. That's the US currency. That's how you buy things. That's how you use things. The US currency, or the currency for the human body, is this. No matter what you're doing, if you are lifting weights, if you are running, if you are rolling over, if you are blinking your eyelids, if your stomach is digesting food, no matter what you are doing, your cells use this. This is the money of your body. So the more of this you have in your body, the more energy you have and the more you can do. So, for example, when I'm doing let's say push-ups, and I can only do X amount of let's say I can only do 15 push-ups. The reason why I can't do 16 push-ups, it's not because my muscles aren't strong enough. It's because at 15, my muscles run out of ATP. Because if the case was strength, what would happen is immediately afterwards, or let's say 30 seconds afterwards, I probably wouldn't be able to do any more, period. But after doing 15 push-ups and I wait 30 seconds, 60 seconds, 90 seconds, my ATP in my muscles are replenished, and I can do a few more push-ups, right? So this is what drives all of your daily activities. Everything. So how does this work? Let's take a peek at the anatomy or the structure of it here. What you have is you have adenine. So you have that nucleic, the nitrogenous base, or the nucleotide, excuse me. Same A found in your DNA and RNA. We combine it with a sugar, ribose, same sugar found in ribonucleic acid, and then we combine it with 3 phosphate groups, and that's where we get the ATP, the triphosphate. So here is what is very cool, unique about this molecule. Take a look at these 3 phosphate groups. These O's right here, that they have a negative charge to them, and in between these bonds, these red lines holding them, there are also negative charges. Well, let's keep it simple. Let's just say the phosphate group in itself, this whole green thing, is negatively charged. And as we know from batteries and just maybe even relationships, opposites attract, right? A positive and a negative like being next to each other. But if you put a negative next to another negative, next to another negative, that's not going to fly. They don't like each other. Alikes actually repel or are repulsed from one another. So what we do here is we kind of create this pent-up energy, if you will. We're not exactly storing it in the bonds, but what's happening is if you put all of these similar charges next to each other, they're going to want to break free very, very quickly. So when we break these bonds apart, specifically when we break this last one apart, what happens is energy is released and it can be used in the cell very, very quickly. And everything in the cell requires energy. Everything we're going to do. We're going to talk about all sorts of crazy things like the Golgi apparatus and lysosomes and active transport and all this stuff. It all requires energy. So what happens is we break apart this bond and our cell's able to use that kind of pent up energy, if you will, for currency, for energy. So the question is, how do we break apart this bond? Well, how did we break apart any other bond with sugars and with lipids and with proteins? And your answer is water, right? Hydrolysis. So we're going to take a water molecule and we're going to snap or break that bond apart, and that's going to allow the cell to use energy. And we'll talk more in detail how oxygen is really, really important in this equation when we get to the cellular metabolism nutrition chapter next semester. We'll also talk about it in respiratory digestive, but you can't live without oxygen. And the reason why is it's not because you can't live without oxygen, is you can't live without ATP. So what happens is if you don't have oxygen going to your cells constantly with every few breaths, your cells stop making ATP. And when your cells stop making ATP, stuff starts dying quickly. And that's why you can only go a few minutes without oxygen to the brain, because your brain cells die very quickly. And when your brain cells die, they don't grow back. And when your brain cells are dead, your brain's dead, your body's dead, unfortunately. So ATP is what's driving everything. Even when you're sleeping, even when you're resting, ATP is what's doing all of the healing. ATP is what's helping with the building and the breaking with the metabolism. ATP is helping your brain figure out how to process all the information with your dreams and just everything. ATP. It's the US dollar, right? If you want to buy a house, you need a lot of US dollars, right? If you want to live on planet Earth, if you want to walk to your car tomorrow morning, you need a lot of this ATP constantly. So how do we get this stuff? We get it from our food. Mainly glucose. Remember, glucose is the preferred fuel source. We want sugar. But we can use fats and amino acids. It's not as pretty and it's not as efficient, but we can use that. But mainly from your foods. So mom and dad weren't crazy. Eat your fruits and veggies. They are good for you. And they'll give you energy. More energy than anything else, pretty much. Okay, last but not least, I want to show you the small structural difference between deoxyribose and ribose, and really that's it. It's pretty much the same thing. They're kind of formed in this pentagon shape, or this pentose, and we are missing one oxygen on DNA, or the deoxyribose, and that's why they call it deoxyribose, because we're missing that oxygen. Sorry, that's supposed to be an O that the ribose has. So make sure you go back to the beginning of the chapter. Make sure you look and focus at those learning outcomes. Hopefully you should be able to answer all those questions. We talked about a lot. We talked about matter, we talked about elements, we talked about water and other inorganic compounds, we talked about electrolytes, and then we talked about the 4 major organic compounds being carbs, lipids, proteins, and nucleic acids. So review all this information. We're going to be building on this. So not to intimidate you or scare you or anything, it's to excite you. We're going to use carbs, lipids, proteins, nucleic acids in the next chapter to build cells. And then we're going to use all those cells to build tissues. And then we're going to build the tissues to build your skin, bones, muscles, brain, guts, lungs, heart, all the cool things that you're probably the reason why you signed up for this class, right? The stuff you really want to learn. We're going to get there. But we got to lay this foundation down first. So, all right, study up. Let us know if you have any questions, and I will see you for Chapter 3.